So vector problems with physics applications. Now remember, we talked about vectors can be representing many different things in physics, right? Like position can be represented with vectors, displacement, velocity, change in velocity, acceleration, forces, right? They could all can be represented by vectors. So here in this case, my vector is representing velocity in this case. So let's take a look how that can be used. All right, so here we go. A plane is flying at an angle of 35 degrees to the horizontal ground at speed of 250 miles per hour. If the sun is directly above, right, overhead, shining straight down on the airplane, how fast is the shadow of the plane moving along the ground? All right. So let's try to understand what they're saying here by drawing out a diagram to illustrate this thing, so we can visualize it. All right. So here's the flat Earth, flat ground, right? And I will be flying 35 degrees. All right, 35 degrees. Now you don't have to do this like this really accurate. I'm only doing this just to show you the visualization of this. So I am flying 35 degrees from the horizontal at 250 miles per hour. So I'm going to say like 1 centimeter is equal to like 50 miles per hour. Okay, so I'm going to draw like 5 centimeters along that direction. So when my plane is flying in this direction like so at 250 miles per hour, so my V is equal to 250 miles per hour. All right, and here is my airplane right here. My airplane is like, I'm gonna be flying in this direction, so I'm gonna just draw my airplane slightly off my arrow so you don't have to. All right, so here is my F-117 stealth fighter. Okay. So as this thing is flying 35 degrees above the horizontal up this way, and sun, right, is directly above. So here's my sun. Sun, Mr. Golden Sun, please shine down on me. Mr. Sun, Mr. Golden Sun, hiding behind that tree. We the children are asking you, please come out so we can play with you. All right, that's enough. So here's my sun. It's shining directly down, which will cause a shadow on the ground, right? So the shadow is right on the ground, and it is moving underneath that plane, right? It's moving underneath that plane at a different speed. So as the plane is climbing up like this, the shadow is like right underneath it. So the speed of the shadow is not going to be 250. Matter of fact, it would be the component, the horizontal component of that V. So here is this is my V shadow, right? This is my V shadow. And this V shadow is really nothing more than just the horizontal component or the X component of my actual plane. All right. So since we know that this is flying at 35 degrees to the horizontal, right? So that's the theta. right? We can use the information given here to calculate the x component of the speed of the airplane, all right? So, how do we do that? Well, we know this is adjacent to my angle theta, and this is the hypotenuse. So you could probably use cosine. So cosine of theta is equal to, right, adjacent over hypotenuse. The adjacent is the Vx, right? So cosine of theta is equal to, right? And hypotenuse is V, right? So we can calculate the Vx. Vx is equal to then, now V times cosine of theta. So Vx is equal to 250 times cosine of 35, and my degrees. So my Vx is equal to 204.8 miles per hour. So that's how fast that shadow is traveling across the ground, on the ground. Okay? So if you want to figure out the velocity, shadow velocity, that would be just 204, right? 0.8 miles per hour x hat. Okay, so this is just one step further than what they're asking. All right. Any questions? All right, good. Next one is going to be very important. So you know what? I'm going to actually put like some stars next to this one. Importante. Very important. All right. So here we go. Here we go. A man walks 2 miles east, right? 2 miles east. So this is going to be the vector A, right? First vector. Then 3 miles north. So this is going to be my vector B, the second vector. And here comes trouble. We have 7 miles, 30 degrees north of west. What? What does that mean? Right? So that's my vector C. To interpret this properly, you have to read it backwards. 7 miles, 30 degrees north of west means from west axis, you're going to go up north 30 degrees for 7 miles. All right? So from west axis, we're going to go up towards north 30 degrees, and we're going to walk 7 miles that way. So keep that in mind. That's very important. So what was his displacement, both magnitude and direction, and component form? Calculate your answer both analytically and with the ruler and protractor. Well, let's do this part first so we can actually visualize what he did. So let's do this part first. Okay, ruler and protractor. So I'm going to say 1 centimeter is equal to 1 mile. That's our scale. Okay. So make sure we know the cardinal points. North is straight up. South is the opposite of that. And right? West is this way, and east, right? Never eat soggy waffles, right? Never ever smoke weed. Public service announcement. All right. So first, we're going to go towards east for 2 miles. So from the origin, we will be going 2 miles to the east, and since I said 1 centimeter is equal to 1 mile, I will go 2 centimeters to the east. Then I will travel, right, 3 miles north. So when I travel 3 miles north from the tip of my first vector, vector A, now notice I'm not using that grid line because notice like I can find my reference line on my ruler and line that up pretty nicely with the vertical axis. Okay. So I will go straight up north 3 miles, so that's 3 centimeters. Right? So this is my B vector. Here's my A vector. Now I have to measure this 30 degrees north of west. So you don't have to do this, but I'm going to do it anyway. I'm going to put a nice horizontal grid line on this so I could actually have some little bit of reference line, right? I'm going to use this B vector as my guidance for my vertical axis. So if I were to measure 30 degrees, right? If I can find my protractor, oh, there it is. So 30 degrees north of west. So from west axis, I'm going to go 30 degrees towards north. So 10, 20, 30 degrees right there. So this is my bearing, right? That's my bearing. And I'm going to go 7 miles along that direction. All right. So here, from the tip of my B, I'm going to go 7 miles along that direction. So here's my 7 miles right here. So that's my C vector. And my resultant will be from the origin, where I started, to the tip of my last vector, which is C. And let's see how that works out. That looks like 7.6 and hair more. Okay? Hair more. So here, I'm going to start from my origin. I'm going to go up to my tip of. So that looks a little more than 7.6, but less than 7.7. So I'm going to split the difference and make that 7.65. Okay, so right there, 7.65. 7.5, 7.6, 7.65. So that's my R. And the magnitude of my R, I'd say 7.65 miles. That's what I measured. Okay, that's what I measured. Now the angle, this angle right here, this theta R, right? What is that? Well, we can measure that out. That looks like 122 right on the dot. All right, looks like 122 on the dot. So my theta R is equal to 122 degrees. All right, so these are measured values, right? So here, the ruler and protractor right here, right? So these are measured. This will be the angle beta, I guess. Right, this will be the angle beta. So now, analytically speaking, now we have to do the analytical part here, I guess. So this is going to be the analytical part. Well, to do that, we need to represent these vectors in Cartesian form, in a component form. So A vector is easy, right? So A vector, we have 2 x hat plus 0 y hat. Similarly, my B vector is easy too, because it's on the axis again. So my B vector happens to be 0 x hat and 3 y hat. Okay, that's easy. However, my C is going to give me trouble because here, this right here is Cx, and this is my Cy. And this is the angle beta right here is 30 degrees. So this is theta C right here. This is the theta C, right? This is theta C. And that theta C happens to be 150 degrees because this is 180 minus that 30 is 150 degrees. So I can calculate now my Cx, and Cx is just C times cosine of theta C. That is Cx is equal to 7 times cosine of 150. Therefore, my Cx comes out to negative 6.06 miles. Then for Cy, Cy is C times sine of theta C. And my Cy is 7 times sine of 150. So my Cy comes to 3.5 miles. So now I have all the ingredients to do the analytical part. All right, so analytical part will be done here. So let's write down the A vector in a component form. So my A is equal to 2x hat plus 0 y hat. And my B vector is equal to 0 x hat plus 3 y hat. And my C vector is equal to negative 6.06 x hat plus 3.5 y hat. So when I add all these up, my resultant vector R, right, comes out to negative 4.06 x hat plus 6.5 y hat miles. So this is my Cartesian form, or the component form of my vector. Okay? So this is the component form. Or otherwise known as the Cartesian form. Okay. Now to do the magnitude and direction, John, you just have to do the Pythagorean theorem to get the magnitude. Right? So here's the magnitude, which is square root of, right, 4.06 squared plus 6.5 squared. Some people actually put that negative in here, and then when they squared it, they didn't square the negative, and then you got like this smaller r value than these two sides. You know that's not correct, right? This is hypotenuse, so it has to be bigger than both of these, right? All right, so if you do that correctly, oh, look at this. You get 7.66 miles, which is like only like pretty close. Look at that. That's really good. Huh? That's like less than like 0.5% error. So this was really drawn accurately. Well, let's see how accurate we really are to figure out what this angle is. So if we calculate this beta right here, then since my r is in second quadrant, we do 180 minus the absolute value of this beta to get my theta r. All right, so my beta is equal to tan inverse of, right, ry over rx. So my beta is equal to tan inverse of ry, which is 6.5, over rx, which is negative 4.06. And if you work it out, you're going to get negative 58.0 degrees. That is this. And since it's going clockwise, it's negative angle. So my theta r is equal to 180 degrees minus the absolute value of your beta, which is equal to 180 minus 58.0 degrees. And that comes out to, wow, holy shnikes, it's dead on, 122 degrees. Boom, boom. So that was really drawn accurately. So my r, if I were to represent that in a polar form, is 7.66 miles, comma, the direction theta r is 122 degrees. So this is the magnitude and direction form. Or otherwise known as the polar form. Booyah. All right. Any questions? I mean, you can also leave this angle, the direction here, as 58 degrees north of west. That also works as well. Okay. So if you say 58 degrees north of west, that also works. All right. Any questions? So I'll leave it up there for you to absorb a little bit. Okay. All right. Moving right along. All right. let's take a look at the next one. Oh yeah, this is kind of important too. So here, a pole has 3 ropes tied to it, all right, with the forces shown for 2 of the ropes, okay? So here is rope 1, okay, with force of 35 pounds of pull, okay? So this is the rope 1. Here's the rope 2, right? Here's the rope 2. Now, calculate the force and the angle. When they say force, how many pounds, right? So this is like, they want magnitude and direction form, right? So they want to know what is the force F3 that would be required by the 3rd rope so that no resultant force is exerted on the pole. So what that means is if I add up all these 3 forces, right, force 1, right, plus force 2, right, plus force 2, plus force 3, if I add all these 3 forces up, the resultant should equal to 0. Okay, that's what they're asking. So I'm going to do this 2 different ways and see which one you like better. You can use either way for your convenience. But just to get the concept going correctly, if I were to pull on, let's say instead of a pole, let's say this is like a rock on a ice, like, right? On sheet of ice. If I pulled this rock this way with 35 pounds, and if I pulled this way at 50 pounds, and if I pull this simultaneously like this, it's going to behave as though only one force is pulling that way. Does that make sense? Right? So if I pull this simultaneously, it's going to behave as though one force is going to be pulling that way, and that force is the resultant force of these 2 forces added. Okay? So let's find the magnitude. Well, we already know the magnitude. Let's find these 2 forces in Cartesian form, or the component form. Okay? So we know F1's easy. Right? So F1, right, looks like 35, right, x hat plus 0 y hat for my F1. That was easy. But what about my F2? Well, if this is 15 degrees right here, right? If this is 15 degrees, then this is my theta 2, right? That theta 2 is 105 because this is 90 degrees plus 15 will give you 105 degrees. Are you okay with that? So I can find my F2x and F2y knowing this angle. All right, so let's do that. So let's find f2x, which is f2 times cosine of theta 2. That is f2x, then it is equal to 50 times cosine of 105. So my f2x is equal to, I get negative 12.9 pounds. Okay. Then, if I were to calculate f2y, f2y is f2 sine of theta 2. Then my f2y is equal to 50 times sine of 105. And my f2y is equal to then 48.3 pounds. So if I add these two forces, it would create a resultant force going that way. If I flip that the other way, that should stabilize it. Okay? So let's add these two forces together. So here, my F1, right, is equal to 35x hat plus 0 y hat. And my F2 is equal to negative 12.9 x hat plus 48.3 y hat. So if I add these two forces up, then I get a resultant force of 1 plus 2. Does that make sense? That force of 1 plus 2 is 22.1 x hat plus 48.3 y hat. That means if I add these two forces up, they're going to behave as though it's going to be going in this direction, like so. Again, I'm not really making this thing like perfect. So here, this is the result of adding these two forces. So this is my F1 plus 2. Okay? The magnitude of my F1 plus 2 is just simply the Pythagorean theorem, which is 22.1 squared plus 48.3 squared. And the magnitude of my F1 plus 2 then comes out to something like 53.1 pounds. So if I apply 53.1 pounds in the opposite direction of my F1 plus 2 this way, I should be able to stabilize this whole thing. All right? So let's find what this angle is right here. This is my theta 1 plus 2. Okay? So to find theta of 1 plus 2, all I have to do is tan inverse of, right, 48.3, so over 22.1. And if I do that correctly, this comes out to 65.4 degrees. So if I apply 53.1 pounds in the opposite direction of my F1, that would be my F3. So now when I add these three forces, they should all cancel out to 0. So my magnitude of F3 should be exactly same as my magnitude of my F1 plus 2, which is equal to 53.1 pounds. Okay, so that's done. But the theta 3, which is this, that is your theta 3. Your theta 3 should be 180 degrees plus your theta 1 plus 2, because theta, this is 180 degrees. This, like, from here to here is 180 degrees. If I add theta 1 plus 2, that gets me my proper angle theta 3. So my theta 3 is equal to 180 plus 65.4. So my theta 3 comes out to 245.4 degrees. So now I can write my F3. So my F3 should equal to 53.1 pounds, comma, direction would be 245.4 degrees. So that would be the answer. Okay. Now, if I want to show you another way, this is just one way. All right. Another way would be, remember this? Once we find our components, right? Once we find our components, we can actually use that. So you could say F2 is equal to like negative 12.9 x hat plus 48.3 y hat. So we can use these information that we found already and then do that. So here we will follow this and say F1 is equal to, right, 35 x hat plus 0 y hat, and F2 is equal to negative 12.9 x hat plus 48.3 y hat, and F3 is equal to F3x x hat plus F3y y hat, And when I add all these up, I should get my resultant. And my resultant basically comes out to, right, 0 x hat plus 0 y hat is what it says. So if I were to take a look at just this, just the x column, right, and analyze that, I should have 35, right, minus 12.9 plus f3x is equal to 0. That should say, okay, well, if I solve for my f3x, then my f3x is, bring this to this side, becomes positive 12.9, bring this to the other side, then it becomes negative 35. So this becomes negative 22.1 pounds. And if I take a look at this, right, then I can say 0 plus 48.3 plus f3y is equal to 0. So if we solve for f3y, then we get f3y is equal to just negative 48.3 pounds. Then we can simply write f3 as, right, negative 22.1 x hat minus 48.3 y hat pounds. And look at that. That is exactly the opposite of my F1 plus 2. This is negative 22.1. This is positive 22.1. This is negative 48.3. And this is positive 48.3. Okay? And finding the magnitude, you already know how to do that. So all you have to do is just do square root of 22.1 plus 48.3 squared. And when you do that, you will get, again, 53.1 pounds, right? And of course, the angle, you already know how to do that angle already, so. Okay? You could find this beta and add 180 to it, and you should be able to get that angle. Any questions? All right. Moving on. So I don't know which one you like better, like this way or this way. I think they're about the same. Okay, they're about the same. So it's the same difference. The answers are the same, but the methods are slightly different. Okay, so moving on. So if a force F of 300 pounds is pushing on a flat surface at an angle of 25 degrees as shown, how much of the force is acting along the surface? So how much force is acting along the surface? And how much of force is acting directly down into the surface? Okay. So we're looking for, so this force right here is 300 pounds acting straight down onto, well, not straight down, but at 25-degree angle to the horizontal surface table, right? So this is 300 pounds of force. That's the magnitude of my force. They want to know how much this force is acting along the surface. So if I have like, let's say, sandpaper or something, and I'm trying to like push it down at an angle, so how much is that sandpaper acting this way, and how much is the sandpaper acting that way by the given force given. All right. So simply, if I were to find the horizontal component of my F, the horizontal component of my F is, this is Fx, right? This Fx is the surface along the surface, okay? And into the table, down into the table, that is my Fy. And if this were the origin, right? Then I guess this would be the origin. Then since this is 25 degrees right here, right? This from here all the way around is my angle theta. And since if this is 25, then this has to be 25 because, transversal cutting through two parallel lines will create, alternate interior angles that are congruent. Remember from your 5th grade geometry class? Right? This is Conestoga. Everybody learns geometry 5th grade. And therefore, that this is 25 degrees, which means this whole angle here, the proper angle, theta, this is then 335 degrees. Are we okay with that so far? Now it's easy. Right? Now it's easy. Because all you have to do is now just find the components. So to find the fx, right? To find the fx, your fx is equal to basically f times cosine of theta. Therefore, your fx is equal to 300 times cosine of 335. So your fx comes out to 271.9 pounds. So your fx vector, right, your component vector, will be 271.9 pounds x hat. Okay. Similarly, to find Fy, Fy is equal to, right, F times sine of theta. Therefore, your Fy is equal to 300 times sine of 335 degrees. So your Fy is equal to negative 126.8 pounds. So if you want that as a vector, your Fy component vector would be negative 126.8 pounds y hat. Booyah. Done. All right. Any questions so far? All right, got one more left. One more. And then we're finished with chapter 3, part 1. We will start chapter 2 next week on Wednesday. All right? Because I guess we don't meet on Monday. No, Monday we're off. Tuesday, I guess you don't have class. And then Wednesday we'll meet. All right, so last page 24. All right, this sounds really complicated when you really read this thing, but when you read it, it's really not that bad if you analyze it correctly. Okay, let's take a look. So here it says a rocket is moving vertically upward with speed of 2 kilometers per second. Okay? So if the rocket is moving vertically upward, right, at 2 kilometers per second, well, that's cool. How fast to the right would the thrusters have to make the rocket go if you want the rocket to travel at 20 degrees to the vertical? So even though the rocket's going like this, it shoots the thruster, retro boosters to the side to make it rocket go like this at 20 degrees from the vertical. So what we need to do is we need to draw this thing out, right? That's the best thing to do, is to draw it out. So here, I'm going to draw my vertical axis. And I'm going to draw my horizontal axis. I'm going to draw my horizontal axis. And the rocket is actually climbing at 2 kilometers per second. So I'm going to say, I'll make it big so you guys can all see it. So here is rocket is climbing here like this way at 2 kilometers per second. But that's a pretty fast speed, right? So my Vy is equal to 2 kilometers per second y hat. However, rocket is not actually going in that direction. It's going 20 degrees from the vertical to the right. So this is the actual path of the rocket. So the rocket is actually going in this direction, right? In this direction. The rocket is going in this direction. And it has to shoot a sideway retro thruster going this way, so the rocket would actually fly horizontally in this direction, so that this is the Vx, right? So that it actually takes this path right here. Okay, so this is the actual path this rocket would take. This is the actual path that rocket would take. So this is the actual V. We need to draw our rocket ship right here. So we're going on a trip on our favorite rocket ship, zooming through the sky. Oh, come on, where's my chorus? We're going on a trip in our favorite rocket ship, zooming through the sky. Oh, come on, you guys suck. Thank you. Thank you. Get on board. We're ready to explore. There's too much to find. Ah, fine. I'm sorry? You want to say what your answer is? That's not guessing. That's actually, correct. That's not guessing. That is the correct answer. Nice. Wow. That's pretty impressive, Jack. I am very impressed. Nice. You are the man. So here's my rocket, right? And it's actually firing a side thruster like this so that it actually so it's actually instead of going straight up, it's going like that, right? With the sound effect. Right? And this angle here happens to be 20 degrees. Okay? So they want to know, right? Um, how much or how fast would the thrusters have to go to make the rocket go to the right? So they want to know what the Vx is. Okay? Well, that's pretty easy now because this is a right angle right here, and this is the angle 20 degrees. So we can actually figure this thing out pretty easily. So we can use tan theta, right, is equal to opposite over adjacent. Right? Boom. Therefore, tan theta is equal to, right, opposite, which is Vx, and then adjacent is the Vy. Notice it's not y over x here, okay? It's the opposite over adjacent. So my Vx now can be calculated as, right, Vy tan theta. So my Vx is equal to, right, 2 times tan of 20 degrees. So my Vx is equal to 0.728 kilometers per second. So if you want to be a vector, then it's 0.728 kilometers per second. X hat is how fast the rocket has to go horizontally. So we know that now V is equal to, right, Vx plus Vi, right? So here they want to know what would the overall speed of the rocket be? So what they want to know is they want to know what the magnitude of my v is. That's what they want to figure out for overall speed. Just the magnitude. Okay. So we can figure out that v is equal to, you can say 0.728 x hat plus, right, plus 2.0 y hat, right, kilometers per second, right? So since they want to know the magnitude of that, all you have to do is find the Pythagorean theorem of 0.728 squared plus 2.0 squared. And if you get that, your magnitude of that v would be 2.13 kilometers per second. That would be the speed of the rocket. So if you really want to find the final v, it's like 2.13 kilometers per second, comma, theta for the rocket. Theta for the rocket is this. This is the theta for the rocket. Is 70 degrees. And that's how we use vectors to solve physics. Next week, we're going to get into one-dimensional motion using vectors. Then, after that chapter, we're going to come back to chapter 3, part 2, and we will use two-dimensional motion using vectors. And that's why we need vectors. Any questions? That concludes chapter 3, part 1. Okay? So, if there are no questions, then here's what you need to do for this. What you need to do is you need to go to the current unit that we're working on in Schoology. Then go to chapter 3 honors vectors part 1 of 2 folder. And if you go to chapter 3 test, there will be vector quiz 3A 2020. Right? And there are 2 problems. And one is, look at this, ready? A man walks 3 miles west. Oh, instead of east, he's going west. Oh no, this is so hard, right? Then 6 miles south. Oh my God, it's not going up north anymore, right? So hopefully you can do this, okay? Then the second problem is worth 10 points. A pole has 3 ropes. Oh my God, 3 ropes. This looks so hard. Never seen this problem before, right? We see the 2 of the ropes here, right, with different pull, right, with different angles. Find the 3rd rope. That's all it is. All right, so print this out, and let's get to work. Hopefully you can upload this by end of the period. If not, then definitely by midnight tonight. That should be more than enough time for everyone, right? Midnight tonight. And if you really, really need an extension on top of that, I'll even give you that. How about like Saturday midnight? But that's really pushing it. Because I'd rather you get this out of the way tonight so you can actually relax the 3-day weekend, right? So get it out of the way today. So let's go. Let's print it out. Come back. Turn your cameras on. This is when I'm supposed to like walk around the classroom and watch you work, and make fun of you and stuff. But I guess I can't really walk around and stuff. I'll just still make fun of you though. But I'll still. So print it out and then work this thing with your camera on so I could take a look at you. Let's go. Oh my God, I only have two students in my whole class. Oh, that is so sad. I only have two students. Oh, one's gone. Uh, oh, another one came in. All right, I'll stop the recording.